Hello everyone, this is Li Wei. In today's lecture, I'm going to show you how to construct Bode plot. So first, let's look at Bode plot construction strategy. Bode plot construction strategy. So in summary, how do we construct Bode plot? So given a very complicated transfer function, so we want to construct Bode plot. Basically, Bode plot include two subplots. The first one is magnitude plot. The second one is phase angle plot. So the standard procedure here I want to introduce is, so if we look at step number one, so first, given the very complicated transfer function, first we want to manipulate it into standard form with 7 factors. We have introduced in the class 7 basic transfer functions. So these 7 basic transfer functions are like basic building blocks. They are like Lego pieces. So if you know how to construct 7 basic transfer functions, they are Bode plot, we can reuse these 7 factors to build up very complicated transfer function. So first, we need to massage the complicated transfer function into these 7 factors. So I will show you an example for that. So the second step is to construct the Bode magnitude plot. So in order to do that, because the Bode plot magnitude, normally they are represented in decibel value. So we have to take log base 10 magnitude of the transfer function. So this is the magnitude in dB value. So because the transfer function h omega is complicated, and we factorize it into numerator polynomial and the denominator polynomial. So for numerator polynomials, they are composed of 7 factors, and for denominator polynomial, they are also composed of multiplications of these 7 factors. So if we take logarithm, that means the logarithm can convert multiplication into addition, or the logarithm can convert division into subtraction. So this is very nice, very desirable feature of logarithm. So basically, so we need to sum up the dB values, the dB magnitude of each factor. So that means, for example, the total dB value is equal to 20 log base 10, the dB value of the first factor, plus 20 log base 10, the dB value of the second factor, and so on. So the third step is to plot the phases. So we need to compute the phase of each factor and sum up the phases. So the total phase of the transfer function, the total phase angle of the transfer function is equal to the phase angle of each factor, and we sum them up. So in order to show how to use the procedure, I want to first present example number 1. So let's construct the Bode plot. the Bode plots. So we have magnitude plot and phase angle plot for the following transfer function. So the transfer function is h omega, so it's function of frequency, so it is 200 j omega over j omega plus 2 times j omega plus 10. So this is the transfer function. Okay, so let's apply the first step. So for the first step, so we need to massage the complicated transfer function into standard form with 7 factors. So you see here, so for the numerator polynomial is already factorized, and for the denominator polynomial is also factorized. So we have factors, but these factors are not in the standard form. So for the standard form, for each factor, the zero order term, so j omega is independent variable, is a complex frequency variable. So the zero order term here 2 and 10, so they are not 1. So if you remember, for the 7 factors, the zero order term are always 1. So first we have to make the zero order term to be 1. So that means, so for the first term, so we have to divide it by 2 for the numerator and denominator. So we have 100 j omega. We have 1 plus j omega over 2. So we make the zero order term to be 1. So for the second one, so also the zero order term is not 1. So we have to make the zero order term to be 1. So that means we have to divide it by 10 for the numerator and the denominator. So that means we have 1 plus j omega over 10, and we divide it by 10 for the numerator, so we have 10. So 10 times. Now you see here, so we have the standard form. So how many basic factors do we have? So we have 4. So first we have 10, which is a constant. So the second factor here we have j omega, which is the so-called 0 at the origin. 0 at the origin. So for the third factor, so we have 1 over 1 plus j omega over 2. For the last factor, or for the fourth factor, it is 1 over 1 plus j omega over 10. So here, so we have the first factor here. So this is the first factor. And we have the second factor. We have the third factor, and we have the last factor. So let me choose a better color here. So let me choose, okay, let's choose green. Let's choose blue. Okay, we have factor number 4. So now let's look at Bode plot for magnitude. So for Bode plot for magnitude, so we have choose the dB value. Okay, so let's look at the magnitude of the transfer function in terms of dB value. So by the definition, decibel is 20 log base 10 of the magnitude of the transfer function, and this transfer function is h omega. So basically it is equal to 20 log base 10. So here we have 4 factors in multiplication. So if we take logarithm, that means the dB value will be sum up. So we have 20 log base 10 plus 20 log base 10 j omega plus 20 log base 10, 1 minus 1 over 1 plus j omega over 2 plus 20 log base 10, 1 over magnitude of 1 over 1 plus j omega over 10. So here we need to take magnitude for each factor. Okay, and then we take the dB value and then we sum up the dB value. So the next step, so here we can see here this is the dB value for the first factor. This is the dB value for the first factor, and so this is the dB value for the second factor, and this is the dB value for the third factor, and this is the dB value for the last factor. So first, let's identify each factor. So the factor number 1 is the so-called constant. So factor number 2 is the so-called 0 at the origin. Factor number 3 is the so-called first order pole or simple pole. Factor number 4 is the so-called simple pole or first order pole. Okay, so for factor number 3, so for the simple pole, so we noticed the corner frequency is equal to 2, and for factor number 4, the corner frequency is equal to 10, right? So this is something that we have to know. Okay, so now we need to build up the Bode plot for each factor. Okay, so here I have already the Bode plot. So let's see how do we draw the Bode plot for factor number 1. So it is a constant. So basically 20 log base 10, 10, so is 20 dB. So log base 10, 10 is 1. So it is 20 dB. So we can plot factor number 1. So this is factor number 1. And let's plot factor number 2. So factor number 2 is a 0 at the origin. It's a linear line. It's cross the frequency axis at frequency is equal to 1, and it is a linear line with the slope 20 dB per decade. So this is factor number 2, Bode plot for magnitude. So let's look at factor number 3. Factor number 3 is a simple pole or first order pole. So for first order pole, the Bode plot, we have two asymptotic lines. The first asymptotic line is 0 dB. The second asymptotic line is a linear line. Is corner frequency is omega is equal to 2. So the linear line will go across frequency equal to 2, and it has the slope of minus 20 dB per decade. So the first asymptotic line is 0 dB. So the corner frequency is 2. The second asymptotic line is the linear line with the slope minus 20 dB per decade. So this is the so-called simple pole or first order pole. Okay, so let's look at the false factor. So this is the third factor. The third factor. So let's look at the false factor. For the false factor, so this guy is also the so-called first order pole or simple pole. So basically for simple pole, we know we have two lines, and the two lines are crossing, the two symptotic lines are crossing at the corner frequency, and the corner frequency is equal to 10. So here basically let's first identify the corner frequency at 10. And so the first asymptotic line is 0 dB when frequency is really low. Okay, so the second asymptotic line for this first order pole is a linear line with a slope of minus 20 dB per decade. It crosses the frequency axis or omega axis at corner frequency, which is equal to 10. So the slope is minus 20 dB per decade. Okay, so this is number 4. Okay, so we need to sum them up. We need to sum up the dB value for the 4 factors so that we can get the total dB value. So let's see here. So how do we sum up? So basically we see here from the Bode plot. So you see here the red line is the summation of the 4 factors. So in the beginning, so we have factor number 1, factor number 2, the dB values will be summed up. So that means basically it is equivalent because factor number 3 and factor number 4 in the beginning they have 0 dBs. So effectively, so factor number 2 will be shifted up by 20 dB. So basically, so factor number 1 plus factor number 2, so we start from here and we move upward until here, until we reach to the first corner frequency at 2, omega is equal to 2. So when omega is larger than 2, factor number 3 dB value won't be 0, and the factor number 3 dB value is decreasing. So that means basically we have to bend from the original curve. So we have to bend 20 dB per decade so that we can consider we can take into account the Bode plot of factor number 3. Or in other words, factor numbers 2 and factor number 3, so the slope cancels. So we have 0 dB slope. So it's a straight line. Until we reach to omega is equal to 10, then factor number 4 will come into effect. So factor number 4 gave us a minus 20 dB per decade slope. So we have to bend our line again to minus 20 dB per decade to consider factor number 4. And then we go downward with a slope of minus 20 dB per decade. So we see here, so the red line is our final Bode plot, which is the summation of the 4 factors dB values. Okay, so this is the magnitude plot. So let's look at the phase angle plot. Okay, for phase angle plot, so the phase angle of the transfer function, the total phase angle of the transfer function, let's look at the 4 factors. So factor number 1 is a real number. The phase angle is 0. So for factor number 2, the angle is 90 degree because it's j omega. It's the angle is 90 degree. So let's look at factor number 3. So for factor number 3, so it's a first order pole. So the angle basically can be represented by, so because of first order pole here we have 1 over a complex number. So that is equivalent to say that the phase angle is minus inverse tangent function. So this inverse tangent function is the phase angle of the denominator, which is a complex number. So the phase angle is, so inverse tangent function omega over 2 versus 1 or divided by 1. So it is inverse tangent function omega over 2. Okay, so minus, so the false factor basically is also first order pole, the phase angle of the first order pole is equal to minus inverse tangent function here y over x. So y here is omega over 10, x is equal to 1, so tangent, the phase angle of the denominator is omega over 10. So it is omega over 10, and we take inverse tangent function, we get the phase angle of the denominator, we add minus 1 is the phase angle of factor number 4. Okay, so now we are going to first plot phase angle for each term. So we have here, so term number 1, let me use another color here. Let me use green color. So phase angle for 90 degree is a constant. Term number 1 is a constant 90 degree. So term number 2, phase angle for term number 2, including the minus sign. Okay, so phase angle for term number 3. Okay, so we have 3 terms. So for phase angle for term number 1 is constant 90 degree. Okay, it's a constant. So for phase angle of term number 2, so remember, so it is from a first order pole, and depending on frequency here omega, so we have first corner frequency is omega is equal to 2. So first let's put corner frequency omega equal to 2. So here at omega is equal to 2, so when omega is equal to 2, so we have inverse tangent function inverse tangent function 1, omega equal to 2, 2 over 2 give us 1. So we have inverse tangent function 1 is 95 degrees, is 45 degrees, so we have minus here, so we have minus 45 degrees. So we have minus 45 degrees here. So when frequency is really low, the phase angle is 0. So how low the frequency should be? So when the frequency is lower than 10 times of the corner frequency, that means when frequency is lower than the 10 times of the corner frequency, the phase angle is 0 degree. So when frequency omega so is higher than 10 times of the corner frequency, or when omega is larger than 20, so when omega is larger than 20, so that means, so this guy is really large, omega over 2, when omega larger than 20, so this guy is really large. Inverse tangent function of this guy will be 90 degree. And then you have minus sign, that means it's minus 90 degree. So when frequency is really large, so we have minus 90 degree. So we can connect them. Okay, so this is factor number 2. So let me use blue color. So factor number 2. Corner frequency is equal to 2. Okay, so let's look at factor number 3. So for factor number 3, it's very similar to factor number 2. The difference here is the corner frequency is 10. So the corner frequency here is 10. So when omega is equal to 10, so basically the phase angle is minus 45 degree. So when the frequency is 10 times smaller than 10, which is 1, So this is the lower frequency bound. So the phase angle is 0 degree. So when the frequency omega is larger than 10 times of the counter frequency, or when frequency omega is larger than 100, so we have 100 here. So when omega is larger than 100, so inverse tangent function will be 90 degree, and we have also minus sign here, we have minus 90 degree. And then we can connect the 3 points. So we get the phase angle for term number 3. Phase angle for term number 3. And then we sum up 1, 2, 3, the phase angles. So we start from 90 degree. So we start from 90 degree because in the beginning 2, 3 have 0 angle. So until we come to 0.2, when omega is 0.2, so we are going to bend here until we reach to the second frequency, which when omega is equal to 1, we need to bend again. And we go when we reach to when frequency is equal to 20, so we have to bend again. Okay, so until when we reach to frequency is equal to 100, so the phase angle will be minus 90 degree.